This is Chapter 5. Welcome to the second unit of this semester. You've probably already taken your first test before watching this. I hope you did well, and we will talk about how we're going to get those grades out to everybody as quick as we can. But this is starting a new section, and this section is all about energy. How does life on this planet get its energy? How is it stored? And then how is it broken down to release energy again? And so this chapter starts off with a toast to alcohol dehydrogenase. I always talk about this just because students don't realize that, college students typically like to imbibe every now and then. But alcohol is a poison. There's no other way around it. And if your body doesn't break down that poison, then you will die. And so you have an organ in your body called the liver, and the liver will take that ethanol, which is poison, and will break it down so that it's not poison anymore. And so there's an enzyme that does that. So thank your liver that it gets rid of those poisons that you actually drink on purpose. But your liver doesn't let you get off easy. It converts ethanol into another substance. It won't kill you, but it'll make you feel like crap the next day. That's why there's hangovers, because your liver has taken something that would kill you and changed it to something that will just make you feel bad. So your liver doesn't let you get off easy. But however, every time your liver is doing this, it starts to cause damage, and it can cause a lot of harm over time. So ethanol breakdown interferes with normal processes of metabolism in the body and in the liver. It harms liver cells, and so fats that tend to accumulate as large globules in the tissues of heavy drinkers, and they can lead to alcoholic hepatitis or cirrhosis of the liver. Now, cirrhosis of the liver it's a nasty little thing, and I've been by the bedside of people who have passed away from this as a minister. It's not a good way to go. Here is a good healthy liver, nice and brown and full of, it filters out the blood. Here is a liver with cirrhosis. And so it just can't function. And if it cannot function, you will not live long after you get cirrhosis. But we're going to be talking about energy. Energy is all important. All of life organization requires ongoing inputs of energy. How do we define energy? Well, you can see here it's just the capacity to do work. One form of energy can be converted into another form. It cannot be recycled, remember. But energy will include, light, and heat, electricity, motion. We call those kinds of energy kinetic energy. Kinetic energy is energy in motion. Energy that is stored in chemical bonds, we call that potential energy. And so we define energy as the capacity to do work again. One form of energy can be converted to another. So there's that kinetic energy, here's the potential energy. This is basically just a repeat of what we just covered. But I like this picture. Here is potential energy. There's a bond there, right? There's a bond, and that's this rope. So there's a lot of energy being stored there in that rope. What happens if we would cut that rope? The energy would be released, and it would be really bad news for him as he plummets down to his death. But that is potential energy. We can easily convert that into kinetic energy by just breaking that bond. And that's what we're going to be talking about in the next two chapters. Forming bonds and breaking bonds. Forming bonds to store energy, breaking bonds to release energy. But first we need to go over these laws of thermodynamics. The first law of thermodynamics says that energy cannot be created and it can't be destroyed, but it can be transformed from one form to another. So we can't make new energy. The second law of thermodynamics, unfortunately, tells us that energy goes from a concentrated usable form to a form that is not as usable or it cannot be used. So that is entropy. It's a measure of dispersal of energy in a system, and it increases just by itself. And so the entropy of two atoms decreases when a bond forms between them, so it stabilizes them. But every time energy transfers, some of it disperses. And as we talked about, usually as heat. So here's just an example. Here is concentrated energy in a pan. You put a skillet with some water in it. You heat it up. So that energy is concentrated here. What happens when you turn off the energy? It will eventually disperse throughout the entire kitchen. So the pan will cool off. It heats up the area around it, and it just moves out. So it's not as usable. You can't cook things in a pan like this. You could when it's over here. So energy will naturally go through entropy. Here's some other, I don't know if it's bad news, but only about 10% of the energy that you take in as food, as living organisms take in as food, only about 10% of it is used to build up body mass, to make things. About 90% of it is lost, and most of it through heat, through these energy conversions. But as we talked about in that first chapter, even that's important, because we've got to keep our internal temperature hotter than the temperature on the outside so that our enzymes will work to their best capability. So energy flows one way. The total amount of energy available in the universe is always decreasing. Remember, you can't create energy. So every time energy is transferred, some energy escapes as heat and is not usable for doing work. Our Earth energy begins with the sun, and we talked about this in that first chapter. What is the source of all of your energy? Every time your heart beats, every time you move a muscle requires energy. Where did that energy come from? It came from the sun initially, and then it was trapped by plants to form sugars, and then we get that either by eating the plants or eating the animals that eat the plants. But we all need a constant input of energy. We have to have energy to keep functioning. Every time your heart beats, it takes energy. And so you got to have a constant source of energy for you to stay alive. We're back to our little energy pyramid thing here, but I put this back here just so you can show this is a pyramid. The producers are down here on the bottom, and you can see there's a lot more producers than there are anything else. So only about 10% of the energy that they capture from the sun and make as sugars will be passed on to this first trophic level here to the primary consumers. So that's why there's much fewer numbers of consumers than there are producers, because only about 10% of that energy is passed on. And then when the secondary consumers eat the primary consumers, only about 10% of that energy will be passed on. And as we go throughout through the pyramid, and you can see most of that energy is being lost as heat. And so here's this from the first chapter again. Energy flows in, it cannot be recycled. And as it flows in, it disperses. That's that second law of thermodynamics. For test number 2, make sure you know the definition of the first law of thermodynamics and the second law. So the question will be, this law of thermodynamics states that, and then I'll give you the exact definition that was on the PowerPoint, so you just have multiple choice, have to pick out the right one. All right, so as we go through these chapters, chapters 5 is basically just laying the groundwork for chapters 6 and 7. Chapter 6, photosynthesis, capturing sun's energy, then put it into bonds. Chapter 7, which is respiration, which is breaking apart those bonds to get the energy back out. So even plants don't use sun as energy. They capture the energy in sugars, and then they break apart sugars just like we do to get their energy. So we're going to be talking about reactions. A reaction is a chemical change that occurs when atoms, ions, or molecules interact. You have a reactant, 2 things that come together, or 3 things, or 4, but they come together in a reaction to form something new, which is the product. what is at the end of the reaction. And so here's just your basic everyday reaction. We have two hydrogen molecules, elemental hydrogen, H2, and we have two oxygens. And when we put those together, what do we end up with? The product is two molecules of water. So the reactants, hydrogen and oxygen, the products, water. But this is the arrow shows the direction that the reaction is going. So we start off with the reactants and end with the product. All cells store and retrieve energy in chemical bonds of the molecules of life. Remember, we talked about the molecules of life 2 chapters ago. So, those carbohydrates for energy, lipids for energy, proteins to do work and to make structures, nucleic acids. So we don't use nucleic acids for energy, but we do use those. By comparing the bond energies of reactants with those of products, we can predict whether a reaction requires energy to go in or if the reaction is going to release energy. Endergonic means energy in, it goes ender. So endergonic means energy in. That's reactions that require more energy than it puts out. This is going to be chapter 6, photosynthesis. It takes sunlight energy in and doesn't release it. It puts it into bonds. So a lot of energy goes in, very little comes out. Exergonic reactions are the exact opposite. Not much energy goes in, but a lot of energy comes out. This will be chapter 7, respiration. As we break apart sugars for energy, it takes just a little bit of energy to get that started, but then it releases a whole lot of energy so that we can live and function. So here is endergonic, exergonic. This is what our next 2 chapters are. Here is energy in. So the sunlight combines with carbon dioxide and water, and that energy goes in and it forms glucose. Now, what happens for an exergonic reaction? So here's all that energy trapped in these chemical bonds. So it adds with oxygen, so our reactants is glucose and oxygen. And what do we get out of it? Carbon dioxide and water, the exact 2 things that we put in, but we get a lot of energy out. So energy is going out for exergonic, going in for endergonic reactions. Now what is activation energy? It's the amount of energy needed to get a reaction started. Some reactions require a lot of activation energy, others do not. It actually takes quite a bit of energy to get sugar to start to break down. I don't know if y'all know that when they opened up King Tut's tomb, they discovered a pot of honey in that tomb. That was still just as good as it was on the day that it was put in there. Sugars will not break down by themselves. It requires some energy going in. So how do we going to get energy to break down sugars? In lab I have a set of slides where we talk about, both of my sons love soccer. I'm just not a big soccer fan. I like American football, where there's a lot more action, a lot more scoring. But I know soccer is so popular. But to me, as slow as soccer is, if it wasn't for enzymes that we have that would lower this activation energy, in order for you to build up enough energy to kick the soccer ball once would take you about a year. So you think soccer's slow now. If we didn't have a way to overcome this activation energy to get the process started, then man, it would be really slow. A year to kick the ball once. So activation energy is going to be critical as we go through this. So here is your reactants, and a little bit of energy goes in, but you'll notice that you're going to be getting a lot more out. So this is an exergonic reaction here. So the way I've always viewed this, and when I usually will draw this out in class, I have a whiteboard. Just draw a stick figure right here, man, and there's a big rock. Now, to get that rock to move down the hill, he's got to push it over this little hill. He's just not strong enough. He cannot push that big boulder over that big hill. Now, he'll get a lot more energy out of it once it starts rolling. I mean, if there's something down here he wants to destroy, there's going to be enough energy to do that. But he can't get it started. He just doesn't have the energy. That's like us trying to break down sugar on our own. We just can't do that. We don't have enough energy. So that's why we're going to talk about here, just the next slides, is we introduce proteins called enzymes. Enzymes are catalysts. And what they do is they lower the amount of activation energy. So instead of this big hill to push the boulder over, it's just a little teeny hill. He does have enough energy to get that rolling just that much, and then once it goes, he'll get all that energy out of it. So activation energy can slow reactions. Enzymes can lower that activation energy to get this thing going. So here's our endergonic reaction. This is the same information. This is repeated again. Learning comes through repetition, and so your book likes to keep repeating things again and again with these. So energy in for endergonic reactions, energy out for exergonic. So here's the enzymes. They are catalysts. An enzyme makes a specific reaction occur much faster than it would on its own, with much less energy. I don't even like that much faster. It just decreases the amount of energy needed to get the reaction moving. Enzymes are not consumed or changed by participating in the reaction. The same enzyme will start one, release, and go to the next, and start that one. Release and start that one. Most are proteins. Some catalysts are RNA. The vast majority proteins. What is the substrate? The specific reaction acted on by the enzymes. Enzymes lower the activation energy required to bring on the transition state. What's the transition state? Let's go back to this thing. When the rock starts rolling by itself. So it takes energy to get it going, but once it starts going downhill, it's going to go by itself. So once you have to stop putting energy in and energy starts coming out, that is the transition state. Active sites on enzymes. Locations on the enzyme molecule where substrates bind and reactions proceed. And so it's how does it lower the activation energy needed? It does it by these active sites on the enzymes. And we'll give you some examples of this, but they just make it much easier for this reaction to start. Lowers the amount of energy needed. So here is an enzyme. This is an enzyme hexokinase this is the first step of your body for breaking down sugar. So you'll notice it's got a little square here. This is the active site. So there's only one thing that's going to fit in that active site perfectly. And that one thing is the molecule glucose. So it fits in there just right, but you'll notice that it's put where this end of the glucose is always sticking out. And this enzyme also facilitates this other little thing here, which is a phosphorus molecule, to come and attach. So the enzyme grabs the glucose, pulls it in, puts its little tail out where the phosphorus can be attached, and it kind of removes water from the system too, so things aren't diluted the way it is. And that phosphorus is able to attach to the end, and then that enzyme will just release that glucose. So now it's out with the phosphorus on it and ready for the next glucose to come in and attach a phosphorus. Why are we attaching the phosphorus? We'll get to that in chapter 7. But for right now, that's just how this works. So it facilitates this reaction. This reaction wouldn't take place on its own. So this enzyme gets the whole thing started. So there's the active site, there's the glucose inside, the phosphorus getting ready to be attached to it. There's the phosphorus meaning the active site. The microenvironment site favors the reaction between the two molecules. Everything is positioned just right for the reaction to take place. And there, the glucose is bonded with the phosphate. It is now no longer glucose, it is glucose 6-phosphate. So we're going to learn when we talk about diffusion, there's no longer glucose inside of your cell, so more glucose will want to come in. Mechanisms of enzyme-mediated reactions. Binding at enzyme active sites may bring on the transition state by 4 mechanisms. First, it helps the substrates get together. Remember that glucose is brought in, the tail is stuck out, that will take the phosphorus, and it will actually, phosphorus fits into that active site then really, really well. So it brings them together. Orients substrate positions that favor the reaction, so the tail is sticking out, and it brings that phosphate in. Inducing a fit between the enzyme and the substrate. That's what this whole process is. It's the induced fit model, and shuts out water molecules so that things aren't diluted and things aren't washed away through bodily fluids. Now, what can affect these enzymes? We've already talked about this. Raising the temperature and dropping the temperature will increase and slow. That's why our bodies are 98.6. At 98.6, it is warm enough for these things to work at their maximum capabilities. If the body temperature starts to lower, then these enzymes don't work as well, and so the process of breaking down sugar slows down. So when you're out in the cold, you're out in shorts and flip-flops and a t-shirt, and in a blizzard, what happens? You start to get cold, and your body temperature starts to go down. Your enzymes can't function as well. They can't break apart the sugars. They can't do all the other things that enzymes do. And so your energy starts to drop. Your brain can't function right. Your heart is laboring to beat because there's just not enough energy. And so finally you will pass out. And if nothing happens, you will pass away because your enzymes can't break down sugars anymore. That hexokinase can't operate to get the phosphorus added on. Then there's another enzyme that adds a phosphorus to the other side of it. Then there's another enzyme that comes along and breaks that in half, so that you have two pyruvates. And so, all these enzymes, so many enzymes to break down sugar. They can't function if the temperature gets too high, gets too low. If the pH gets too high or too low. Remember that term homeostasis, where your body is going to fight to keep the same standing. So your body is going to fight to keep that standing. So pH will stay the same. Salt levels can also mess up enzymes. Remember, enzymes are proteins. And if they lose their shape, they can't function. If that active site, the shape of it is changed at all, glucose won't fit into that hexokinase. So these things can affect enzymes. In lab, we do an experiment where we show that heat will stop this, cold will stop the reactions, and pH will stop the reactions. And we see the optimal temperatures, the optimal pHs. Guess what the optimal temperature is for enzyme-mediated reactions? It's 98.6. That's no accident that our bodies are at 98.6. It's what we need for these enzymes to work their best. So here is enzyme activity with temperature, and we see different enzymes have optimal temperature, but the colder, the hotter you get, typically the less they are working. Here's one with pHs. We have this pepsin, which is actually a protein in the stomach that starts to break down, especially proteins and milks and things like that. And so that works really well in the stomach. But once we get to the small intestines, the pH is about 7 to 7.2, and so they work best where? Right there. So pH determines how these things will function also. So here's just your take-home message, just a way of the review. Metabolism. ATP enzymes and other molecules interact in organized pathways of metabolism. These are activities by which cells acquire and use energy. So your metabolism is how you are getting your energy. A big part of your metabolism is how you break apart your sugars to get ATP, and also how you are making different proteins to act as enzymes, and hormones, and structural things, and so. So a metabolic pathway is any series of enzyme-mediated reactions by which a cell binds, rearranges, or breaks down organic substance. The next chapter, chapter 6, we're going to be focusing on how the plant can take carbon dioxide and water with sunlight and make a sugar. That's a metabolic pathway. Chapter 7 is how plants animals, fungus can take those sugars and break them apart to get energy. That is a metabolic pathway. Anabolic pathways build molecules. Catabolic pathways break them apart. Cyclic pathways regenerate a molecule from the first step. And we're going to see examples of both of these, all three of these, as we go through the next two chapters of photosynthesis and respiration. All right, concentrations of reactants or products can make reactions proceed forward or backwards. So your body is constantly monitoring. You have recognition proteins on all of your cells that are monitoring everything. So your body knows exactly how much sugar's in your bloodstream. And if there's too much, your pancreas will start to secrete insulin, which will bring it down. And so there is these feedback mechanisms that can adjust enzyme production or activate or inhibit enzymes. Regulatory molecules can bind to an allosteric site to activate or inhibit enzymes, and that is feedback inhibition. Now, what in the world does that mean? Let's take a look at this. Here is, let's just say this, I don't know for sure. Yeah, they're not telling us what this whole process is here. Let's just say this is breaking down sugar. This is one we're going to be talking about a lot. So what is our reactant? Sugar. So remember that first enzyme, hexokinase, grabs the sugar and puts a phosphorus on it, right? Now, so now that they can continue to break down these sugars. So that gives us that intermediate state, that glucose with the phosphorus stuck on it. Then enzyme 2 will put a phosphorus on the other side, which gives us another intermediate. Then we can break that in half, and that gives us the product of the first step of breaking down sugar, which is 2-pyruvates. Now, that would take 3 different enzymes for this process to take place. Now, what if suddenly the cell says, okay, we can't handle any more breaking down the sugar. We've got plenty of energy right now. Let's slow this down. So basically what your body will do is it will release something that will attach itself to that first enzyme, change its active site so that it can't take the sugar in to get this process started. So basically it just pushes pause on this whole process. We've got plenty of energy right now. Stop breaking down sugars. So we put a pause on it. Then what happens when you need sugars? Another signal is released that removes those coenzymes out of here. The active site gets its shake back. It now starts breaking down sugars again. So it starts the whole process over again. That is that feedback inhibition and using of allosteric sites. So what is a redox reaction? It is an oxidation reduction reaction. A molecule that gives up electrons is oxidized. So when it gives over an electron to something else, it becomes oxidized. A molecule is reduced that accepts electrons. So why do we call it reduced? Because it's getting a negative charge. If the charge is reducing, and we'll talk about something else in just a minute. Coenzymes can accept molecules in redox reaction called electron transfers. Now this is going to be the basis for how sugars are made and how we break apart sugars in our body. Here's just an example of a redox reaction. Glucose and oxygen react when exposed to a spark. Energy is released all at once, and then carbon dioxide and water form. So there's a burst of energy. So this is that an endergonic or exergonic reaction? That's exergonic. A little bit of energy in, putting a spark, and then you get a fire coming out of it, a lot of energy coming out. So that's exergonic. But why is this a redox reaction? Well, let me show you this next slide here. This is going to be the basis of how sugars are made and how sugars are broken down. So, all right, let's put it all up there. Energy input splits glucose into carbon dioxide, electrons, and hydrogen ions. So we're breaking apart sugars. Electrons lose energy as they move through an electron transport chain. So basically what happens is this electron is given a boost of energy. Remember we talked about electrons being, happy if they're in full outer shell. Well, you can actually take one of your electrons, give it a boost of energy, and knock it temporarily into the shell above it, so that it has more energy, it's moving faster. It's like your electron suddenly took a couple Monster drinks and drank them. Now he's got all this energy, he's bouncing off the wall. And what happens is he will go through a series of reactions that's best viewed like a staircase. When he goes down the first step, he loses some energy. When he goes down the next step, he loses some energy. When he goes down the next step, he loses some energy until he gets at the bottom of the stairs, and now he's like, I feel so tired again. So now he gets a couple more Monster drinks them, so he gets all that energy back, and then he goes through the process again. As we make sugars, it is absorbing sunlight, activating these electrons, and as it goes down each step, it releases some of that energy that the sunlight gave it, and it uses that to pull in a hydrogen ion. When we break apart sugars, we're breaking apart these bonds, and as that bond is broken, it excites that electron, as he's like all hyped up, and as it goes down each step, he releases a little bit of that energy, and that energy is used again to form ATP, which is our energy unit for the cell. So that's the take-home message. What are some cofactors? And we're going to be talking about this in the next two chapters. They're helper molecules. They help the enzymes function. They will help the enzyme carry out the product, or they will actually mediate the next part of the reaction. So cofactors, atoms or molecules other than proteins that are necessary for enzyme function. Coenzymes, or organic cofactors such as vitamins, they may become modified during the reaction. We'll see that as we deal with these next two chapters. So ATP, this is our special coenzyme. This is what the whole process is about, photosynthesis, respiration. Plants absorb the sunlight, and the ultimate goal is to make ATP. We break down sugars. The ultimate goal is to make ATP. This is the energy unit of the cell. Adenosine triphosphate, it has 3 phosphate groups, and transferring that phosphate group will add energy to it through the chemical bond, or breaking that phosphate off releases energy that your body can use. So what is phosphorylation? That's going to be a great question on the test. It is adding a phosphorus group to a coenzyme. ADP, which is, this is triphosphate, this is diphosphate. Doesn't have usable energy. But when a phosphate is added to it to go from 2 to 3, it then is carrying energy in that bond, and then it can use that, and then it becomes ADP, and then it goes back to get another phosphate, and so these things are used over and over and over again. So here is, a couple of reactions. Here is photosynthesis, the best example, carbon dioxide in the water, energy in, and we get sugars at the other side. Then when we break apart sugars, it's an exergonic reaction, and we end up with the exact same reactants that we started with. They're now products after breaking down sugars. Don't worry about this too much yet. This is not going to make much sense. This will become crystal clear as we go through the next chapters. But this is just showing us that ATP can be recycled again and again and again. It goes from ADP to ATP. And that is what stores the energy for life on this planet. Now, for some reason, your book has put this at the end of this chapter. It doesn't belong here, but they put it there, just to give you a little insight into what the book company does. When they make a new edition, they will take this little section and put it on chapter 4, just so the book is different. And then when they make the next edition, they take this section and put it back here in chapter 5. So it's, they want to keep making new books to make more money, so they can charge more, and so there you go. Why this is here, I have no clue, but let's take a look at it. It is important that we talk about some of the things that happen in the next 2 chapters, but a look at cell membranes. Remember that plasma membrane, that lipid bilayer surrounds every single cell. But it's not just a lipid bilayer, it has all these proteins stuck into it. So phospholipid molecules in the plasma membrane have 2 parts. Remember that hydrophilic heads so it likes water, hydrophobic tails. The fluid mosaic model, what's that mean? You have a plasma membrane around each cell, but the plasma membrane does not stay the same. It's constantly pinching little parts of it off as it releases different things as in vesicles, and it's constantly bringing things in, so it pinches off plasma membranes that comes in and it goes inside of your cell. So your plasma membrane is constantly changing for every one of your over 34 trillion cells. So that's what this model is talking about. The biolayer is a mosaic mixture of phospholipids, steroids, proteins, and other molecules that are completely changed. But it's made up of different things. It's not just that lipid bilayer. So there's the lipid bilayer picture again. We've already seen that in a previous chapter. The cell membrane function happens because there's so many proteins associated with the lipid bilayer. The membrane proteins temporarily attach to the lipid bilayer surfaces by interaction with lipids and other proteins. Don't worry about that. All right, so there's different types of proteins that attach to the lipid bilayer. Adhesion proteins helps cells stick to one another or to an extracellular matrix, so that just makes sense. They're adhesion proteins, but they're stuck to the plasma membrane. There's receptor proteins that initiates a change in the cell's activity in response to a stimulus. So if the cell inside says, hey, we need phosphorus in here, so that will activate a protein, a receptor protein on the outside that recognizes phosphorus, will grab it and then pull it through the plasma membrane so that there's more phosphorus inside. Enzymes are catalysts, and membrane catalysts provide a relatively stable reaction site for many metabolic pathways. There's different reactions that take place even in the plasma membrane. And then there's transport proteins that will move things, grab them and move them into the cell or allow them to leave the cell. And so diffusion. This is going to be an important concept that you need to know diffusion. Diffusion is the net movement of molecules down a concentration gradient. The simplest example I can give you. You get a cup of iced tea. It's unsweetened. You want to add sugar to it. So you add 2, 3, 4 teaspoons of sugar, whatever you're adding to it. Where does the sugar go? It flows to the bottom, right? So now there's a big concentration of sugar at the bottom, very little at the top. By a natural process, that sugar is going to dissolve in the water. Remember, water is an excellent solvent. It can break apart these molecules into smaller molecules. So if you just let that glass set, especially if in the sunlight, to get a little bit of energy going with it too, then that sugar will naturally, so when you come back to it, it's going to be equal parts all over. Salt, this happens much easier. Get a glass of water, put in about 3 tablespoons of salt, look at it, all the salt goes to the bottom, but it starts to dissolve, and by the time, however long it's going to take it to diffuse, there's going to be equal parts of salt at the top and at the bottom. It's a natural process. It moves substrates in, through, out of cells. And a substance diffuses in the direction set by its own concentration gradient. So if you put all the salt in the bottom, it's going to dissolve upwards. It'll diffuse upwards. If you put, like the salt would be floating at the top, it will diffuse down. So it goes from an area of greater concentration to an area of lesser concentration. Depends basically on 5 factors: the size of the molecule, the smaller the molecule, the faster it diffuses, the temperature when you add heat to it. Now, if you're going to make sweet tea, when do you add the sugar? You add it while it's really hot. So if you're going to make enough for it to be sickening sweet, like Southern sweet tea, you add it while as soon as you turn it off, the water is really hot, you got the tea bags in there, you add the sugar because the temperature is going to help that diffuse throughout. Steepness of the concentration gradient, charge, you can actually, some of these things are due to polarity and will help it to go throughout, and then pressure can cause diffusion to take place quicker. All right, semi-permeable membranes. Your plasma membrane is semi-permeable. Some things can go through it, some things can't. Water can go through channels in the plasma membrane, but molecules can't. So the ability of a cell's membrane to control which substances and how much they enter or leave the cell. So your cell membrane gets to pick. That's the whole purpose of your plasma membrane, to pick what comes in and what goes out. You don't want just everything coming into the cell. You don't want bacteria to come in. You don't want viruses to come in. Let me hit the lights here just for a second. So you don't want all these things coming in and out. So your body is able to determine what comes in. So it allows the cell to maintain the difference between its internal environment and external fluids. So you can bring in a greater concentration of stuff inside than outside. Diffusion would say, well, you brought all these things in. Let's say you're pumping in sugar into your cell. Diffusion would say that sugar would want to leave the cell because there's a greater concentration inside than out, but that plasma membrane won't let it. So you're building up a greater concentration inside. The diffusion will not let it go out. It supplies the cell with nutrients, removes waste, maintains volume and pH. Water diffuses across membranes by osmosis. So osmosis here is critical. The molecules can't move across the membrane, but water can. So osmosis is the movement of water down its concentration gradient through a selectively permeable membrane from a region of lower solute concentration to a region of higher. So now suddenly it's lower than remember, diffusion was from higher to lower. That was the particles. Osmosis is not the movement of the particles, but the movement of the water. Because the particles can't move through this membrane, but water can. So what's going to happen here? So let's take a look at this. Here is a semi-permeable membrane. So let's say this is sugar molecules. See over here, let's say this is the inside of the cell. Pumping in all kinds of sugars. Yay, we got all this sugar in here. Now, by diffusion, what's diffusion say? These sugar molecules, I want to come over here and even out over here. So there'll be equal number of sugar here, equal number here. But you've got this membrane here. It's not going to let the sugar molecules come through. So since the sugar molecules can't come through, what's going to happen is water is going to move this way because it wants it to be equal concentration. So as water moves through, it causes more water to come inside, and so more water will come through until there is equal amounts of sugar molecules per unit of water. So water moves. And so if this was a cell, what would happen? Water would be rushing in, and it would cause the cell to get bigger and bigger and bigger. And if it kept going, it would get to the point where the cell would explode. So that's osmosis, water going through that. So selective permeability. We've already covered this. Again, this is just a repeat of what the slide was before. So this is just a little thing. Here's our lipid bilayer. Water, gases, we can move through the channels made by proteins and the lipid bilayer. Larger molecules, can't do it, can't move through. And so it is selective. If it wants to pull a molecule like this in, we're going to talk about here in a minute, there's actually transport systems that will grab it and pull it through. All right, so hydrostatic pressure, turgor, is the pressure exerted by the volume of fluid against the surrounding structure. So remember when we said if this example was a cell, then what's that cell going to do? It's going to start to expand and expand, and that turgor pressure inside is going to keep increasing until the plasma membrane can't hold it, and it's just going to burst. So that is what they're talking about there with turgor. Osmotic pressure is the amount of hydrostatic pressure that can stop water from diffusing into that cytoplasmic fluid or other hypertonic solutions. So tonicity, what in the world is that? So let's say we're using that example where there's a lot more sugar inside of the cell than outside, so the water flows in to kind of equal it out. So if there's, what is isotonic? It's the same solute concentration on both sides. So it's equal. So water's not going to be moving either way. Hypertonic solution is a lower solute concentration, hypotonic. Hypertonic is greater. So over here, let's go back to this again. So this is, remember, this is the inside of the cell. So this is hypertonic. There's a greater concentration of the particulate in there. This is hypotonic. There's not as much. So what's going to happen? Water is going to run from hypotonic into hypertonic to make it isotonic over there to where it's equal. So that's the whole process of osmosis. And we're going to see, that's kind of important as we go through these next chapters. So know the difference between isotonic, the same solute concentration, hypotonic, whichever side of the solution has the lower solute concentration, hypertonic, which has the higher solute concentration. All right, so here's red blood cells. This is what they look like. They look like little donuts. They're concave in the middle. And so this is perfect. This is in an isotonic solution. Now, water diffuses out of red blood cells when immersed in a hypertonic solution. So remember, the water wants to go to make equal solute concentration. So the water leaves, and what happens? The red blood cells shrivel up. This area here is what's going to be carrying oxygen. Can't do it anymore, so they can't function, and so that's bad. Over here is what happens if the red blood cells is immersed in a hypotonic solution. So there's more solutes inside of the red blood cell. Water's going to want to flow in. They're going to expand, 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 even bust. You see there's a couple of them here that have burst open. But these guys no longer have that concave shape, so they can't carry oxygen. They can't function either. So it's important for your body to keep those isotonic relations so that cells can function the way that they need to. So there's turgor again, and that's just a repeat again too. All right, so how do things move across these membranes? So we have transport proteins allow a specific substance to cross. So there's going to be little channels that will allow only certain shaped molecules to pass. And there's some that require energy to where they'll actually grab them and pull them through, and some don't require energy where they can freely flow in and out based on diffusion. Ions and large polar molecules require other mechanisms. But here's passive transport and active transport. What in the world does that mean? The only thing that means is, in passive transport, doesn't take any ATP, doesn't take any energy. Things that naturally are allowed to go through based on the concentration gradient. So diffusion is what drives passive transport. Active transport, well, here's an example. So there's a glucose molecule. So, what's the purpose of glucose? To give you energy. You don't want to be wasting energy pulling it in. So basically what this thing does is it doesn't require any energy. This protein is like this. There's only one thing that's going to fit in the top of it, that's glucose. And when the glucose fits into it, it causes it just to go like this then, so that the glucose is naturally just dropped into the cell. Requires no energy, that's passive. Active transport is when you actually have to grab it and use ATP to either pull it in or push it out. And so here is sodium. This is the potassium sodium pump that's being used in our muscles. And so this takes energy to do it. That's why it takes energy for you to use your muscles. All right, what we're talking about now. Endocytosis and exocytosis. This makes no sense. To me, the picture's worth 1,000 words, especially with these. Pictures are. Exocytosis is things leaving the cell through the plasma membrane. Endocytosis is things coming in, but it all involves the plasma membrane. Here is exocytosis, I'm sorry. So let's say this is a lysosome. Remember, the lysosome is what? The wastewater treatment plant of the cell. Waste is put in there, enzymes put in, and it breaks apart that waste. Now, but it wants to get rid of it. Here's the exterior of the cell, here's our lysosome. So it comes and it has a plasma membrane around it. There's a plasma membrane up here. It just comes and attaches to that plasma membrane so that what's inside the lysosome will then just be emptied out into the cell. So that is exocytosis. Here is two different types of endocytosis. I'm not going to ask you the different types. But this is just regular endocytosis where the plasma membrane will actually pinch off and carry the stuff that's outside, inside. And so here's the stuff outside the cell, the plasma membrane pinches off. Now it's inside. Typically what happens, especially for stuff that your body needs, there's recognition proteins out here that will grab what it needs, and it will actually pinch off. Once it's all full, it'll pinch off that plasma membrane so that it brings those inside of the cell. So that is a endocytosis also. So this is just explaining those two. Phagocytosis happens with amoebas as the plasma membrane reaches out in those pseudopods and grabs something and then pulls it inside. Then it pinches off that plasma membrane as it comes inside. Then it just puts in enzymes in it. That little thing acts like a little stomach. It's called a food vacuole. And it just floats around, releasing sugars and nutrients as it floats around the body because those enzymes are pumped in there. So exocytosis. So new membrane proteins and lipids are made in the ER. Why? Because you keep pinching off and putting new plasma membrane out. So you got to keep replacing all these things. So they're made in the ER, modified in the Golgi bodies. They're put in vesicles, and then those are shipped out with those transport proteins so that they fuse with the plasma membrane. So there they are being made, go to the Golgi body where they're packaged and shipped, and up to the plasma membrane where they become part of the plasma membrane. All right, so that's the end of chapter 5. So now we're ready to begin, to me, what is probably the two most important chapters that we're going to cover all semester. Probably also the hardest, unfortunately. But this process of photosynthesis, the miracle to take sunlight and make sugars out of it. It's amazing that plants can do this. And then the next chapter, breaking apart sugars so that we can get the energy that we need. So we're going to be looking next at photosynthesis. It's one of my favorite chapters. And then cellular respiration, which is breaking apart sugars. So we will see you again soon.